Hi, good afternoon. I'm Martin Fareisen. I'm from the systems group at Dell Technologies, and here I'm going to today to talk about CAE and the latest generation of Intel processors, informally known as Ice Lake. Get my slides to go forward, as they never do. Page down, try that one. So I've been at Dell 6 years now, and as part of the engineering team, we work within Dell, within the product development group, within the CTO office. We work with a lot of customers, and we have a HPC AI and Innovation Lab. And what we've been working on really is to develop what we call validated designs for HPC. If you look at like Hyperion or IDC, you'll see that there's possibly 10 to 20,000 customers in the world using computer-aided engineering to develop products virtually. The plethora of solutions for HPC are widespread, and customers are often just daunted with the task of trying to assemble HPC validated systems that actually work with all the components involved. So at Dell, what we try to do is we try to create these systems, we try to validate them, test them, work them and prototype them, allow our customers to evaluate these systems so that when the customers get the systems, they're all assembled, they're complete validated system, and the customer doesn't have to spend their time doing IT, they can do engineering on their devices. I don't know if you call them masterpieces or not, but in some sense, I think they're really robust solutions, and this is what we really focus on. Again, we have a very large HPC AI and Innovation Lab. I think the top 500 was just announced. I think we were like number 235 on the system with our latest system, but that's just one of our clusters. We have a lot of clusters. It's a really big center. In that center, we do a lot of projects with customers. We let customers onto our sites, but we also work a lot with all the major ISVs, and we really try to validate our solutions. You know, we look at the upcoming processor technologies and network technologies, the storage technologies, visualization, all these aspects, and try to make integrated solutions. What we hope to do is that as we come up with these validated solutions, that as our customers deploy them, they're not on the bleeding edge or the first off, that we can run the same simulations and the same benchmarks on our systems in case they have any issues with their applications performance or quality of their applications, or installing, say, new firmware options or whatever. And so they're just not flying in the dark. So now I'll talk a little bit about the new third generation scalable processors from Intel called Ice Lake. We've been playing with them probably for maybe a year now in the lab. We've been selling them to customers for a while, so I'll try to generally show you the generation performance over the previous processor, the Cascade Lake or the 2 series processors. And for the most part, we just look at a lot of single applications. We understand that most of our customers run generally many of their applications in parallel over multiple nodes, but for the most part, running single node benchmarks takes the network out of consideration, really just focuses down on what the performance of the processors are that can drive these solutions for customers. So an example here is ANSYS Fluent CFX, which is accurate CFD program from ANSYS. And we can see that our new 15th generation hardware with Intel 3rd generation scalable processors, you know, various processors here with different numbers of cores from, you know, so these would all be dual socket processors. So as an example, Intel Gold 6346 processor, which has 16 cores per processor, would have 32 per node. So here the basis of our comparison in terms of performance where higher is better would be the Cascade Lake 6248 processor with 20 cores per processor, 40 per node. And you can see that the previous generation highest power processor was 8280 with 28 cores. And you can see that that offered typically somewhere between a 10 to 20% performance lift over the normal 20-core processor, which most of our customers were using 2 to 3 years ago. And you can see with the 4 choices of Ice Lake from the 6346 to 6336Y, and then the 2 Platinum processors, both with 32 cores each, really offer substantially better performance than what customers were getting on their systems that are 2 to 3 years old, which are probably about 10% faster than the 4-year-old systems which they're replacing. As you can see, across the board here, we're seeing typically about a 1.5x improvement over the Cascade Lake. Fluent's another very popular CFD code from ANSYS as well. And here we see, 5 standard benchmarks from Fluent. Excuse me. Again, this is similar to the last slide, where we're seeing not quite the performance advantage with Ice Lake over Cascade Lake, but still it's very healthy, typically in the 30 to 50% range. We see this universally on a wide set of CFD applications. Dyna is very popular code, and here are 2 public benchmarks, TopCrunch car-to-car and ODM model, a 10 million element model. Again, we see a similar trend here where, again, within the Cascade Lake framework, that the best processor you had was the 8280, which was again about 20% faster than the normal 20-core 6248. And again, we see that the Ice Lake processors are far surpassing that, both in terms of core performance and node performance. Moving on to ANSYS mechanical implicit FEA code. Here there's a lot more standard benchmarks, and again we see the same standard as 1.0 performance is 6248 with Platinum 8280 next to it. And as you're probably well aware, ANSYS mechanical can do a lot of different things. So we have conjugate gradient solvers, Lancho solvers, sparse solvers as well, with a bunch of different ANSYS benchmarks. And then again, uniformly, we see, excuse me, typically a 30 to 50% performance lift with the Ice Lake processors. Now I'm trying to show you a little bit something different. Bar graphs are one-dimensional. I'd like to show something that's two-dimensional, where we look at scatter plots, which basically show the relative core performance and node performance of the various processors. Why go away from that? In dealing with customers, every customer is different, but generally speaking, they're looking for 2 things in processor performance. They're looking to get better job turnaround times and better utilization of ISV licensing costs. And these tend to be pegged to this single core performance. But they also have increasing workloads, and they're looking to generate more engineering per day. And that type of metric is best measured by the node performance. So some customers are more focused on node performance, some are more focused on core performance, but in general, what customers like to do is they like to have better of both. So if we look at a 2D diagram here, and we assume that the existing system would have a node performance of 1 and a core performance of 1, generally, customers would want to be in the upper right corner. Typically, as they go forward, they want the core processor performance to maintain with the previous system and typically get more cores, because core performance is not generally grown as fast as the number of cores in the node performance. And as an example, if a customer was running a Dyna job 256-way parallel on a previous system that had 16 core processors, That would be 32 processors per node. So they'd have to run it over 8 nodes to get to 256-way parallel, and that might take 10 hours. So if they bought a new system, let's assume that it had 32 core processors, they would only need 4 nodes then to get to that same level of 256 core, and they would still want the turnaround time to be of the order 10 hours or less. So that would mean that they'd have to have a core performance of 1. So this is how one would understand these types of charts. So if we look at ls-dyna as an example, here we see a bunch of processors, various Cascade Lake processors in blue, and we see the Ice Lake processors in gold. And you can see that there's a bunch of different processors. As an example, over on the middle left is the 6234 and 6244, which are 8-core processors. So the core speed is very good, but there's so few cores per node that the overall node performance is not particularly good. And we see that there's a wavefront there of what the Cascade Lake technology can give you. And then we see that the Ice Lake technology just eclipses that all the way across the board. So looking at this, what we see is, again, the 6246, which is a 16-core processor, offers extremely good core performance over here the reference is a 16-core 6242 processor. So it's offering basically the same number of cores at 16 per processor, but at about 26% better. So if the customer was just to stay with the same number of cores per node, they would, see about 25% better performance moving up the Ice Lake. Typically, what we're seeing though is that customers tend to want to shift over generationally. So if they were using 16 or 24 core processors with Cascade Lake, they probably would want to look at 24 or 32 core processors with Ice Lake. So something like the 6342 or the 8358, where they get essentially the same core performance as before, but substantially better node performance. So their runtimes would be comparable to what they were on their previous systems, but they could generate almost twice as much work. This is OpenFoam, which is a different code. And what we see here is that unlike Dyna with CFD, sometimes because certain problems are much more memory bandwidth limited than others, that there's generally a much greater variation in the core performance among the different processor choices. So what happens is again, as applications become more memory bandwidth limited, the chart becomes more vertical and less horizontal. But we can see because the Ice Lake processors have so much more memory bandwidth because of the design, they again are moved farther over to the right. So the core performance is not substantially better, and it doesn't really change all that much, but Ice Lake just handles memory intensive applications so much better than Cascade Lake. And Converge is a popular combustion code, computational fluid dynamics combustion code. And again, we see a similar type of behavior where, unlike Crash, where things tend to get spread out a little bit more vertically, within CFD, often it's a little bit more compact. But again, you can see that really Ice Lake provides a new paradigm of performance for customers. Going away from charts and looking at tables now for a bit, talk a little bit about MSC Nastran. I think in talking with customers over the last year, there's been a general confusion about Nastran and other implicit FEA codes that historically customers don't believe scale very well. So historically, they looked for processors that had very few cores and very fast clock speeds. With Ice Lake, it's really not that situation now. What we see is that the core speed is relatively invariant across the whole line of Ice Lake processors, and that what varies is generally how much cache and how many cores there are. So what we're seeing is that customers are starting to move away from, say, 4 and 8 core processors and starting to go to 16 and 24 core processors for implicit FEA codes like Nastran. And as you can see here, looking at 6 different customer benchmark models, different types of solutions where we just have both eigenvalue solvers and different types of frequency response, both with the AMLS solver and the ACMS solvers. And we can see that in general, we're seeing about a 1.5 times speed up moving from the Cascade Lake refresh, which was the 6246R, which is a 16 core, which is really the best processor that we had for implicit FEA. And now virtually all of these Ice Lake processors, regardless how many cores they have, particularly at this model running 16 benchmarks, are fast exceeding that type of performance. And it allows customers to buy more general purpose. If they can buy systems that have more cores, they know that those systems run very well with non-scalable applications that can only use 4 or 6 cores, but some of these applications can use a lot more cores, 40 to 50 cores, and then they would have that available. So in general, the Ice Lake is much more robust than the Cascade Lake at a wider variety of simulation types. And this is, another example of MSC Nastran AMLS. And again, we can see a very large customer NVH problem. I've been working with this customer for 5 years now, and as you can see, they literally started 5 years ago at running this problem in 18 hours. Now with the latest Ice Lake, they're down to under 4.5 hours. And you can see again here, literally almost a 50% improvement moving from very fast Cascade Lake and Cascade Lake refresh processors, the 6246R and the 6252.4, which were the fastest processors at that time. And, we're cutting the time by almost 50%. And talk a little bit about Abacus. This is Abacus Explicit, which a lot of customers use as well. And again, we see the same type of situation again, where, if we look at the 3 bars to the right, which are the Ice Lake numbers, we're seeing between, 1.4 and 1.8, up to 2%, factor of 2 better performance. So, across the board, what we're seeing with CFD, with explicit FEA like Dyna, and with implicit FEA like Abacus, ANSYS Mechanical, and Nastran, we're just seeing, generally 25 to 50 to 60% better performance with Ice Lake over Cascade Lake. So that's the slides I have for today. Thank you for your attention. Pardon the fact I probably shouldn't eat peanuts before I give a webinar, but now I'm opening it up for questions.